interval 0, 1.5 to an accuracy of 0.1. So, first of all, how would you show that the chromosome design that's been chosen will satisfy the accuracy required?
Count the bits. How many zeros?
You'll have to count the bits at some point, but what do you just need to do before that? So, in order to ensure that you've got a chromosome which will be sufficiently refined, you need to look at the range divided by the tolerance and add 1. So that's 1 plus the range is going to be 1.5 because you're going from 0 to 1.5, and the tolerance is 0.1. So that gives you 16. So that means you have 16 possible values of the design variable you need to accommodate. And this is where you count bits, because that has to equal 2 to the n, where n is the number of bits. Because each bit, of course, can have a 0 or a 1 as its value. So 2 to the 4 is 16. And so these chromosomes, which clearly have 4 bits, will give you the required accuracy. So that's always the first step in a GA. Make sure your chromosome can deliver the tolerance you've specified. So, at that point, it's really filling in the table, and this is really only if you're going to do it by hand, and the only place you would do that is an exercise or an exam question. So, give me the values, column by column.
It's solved.
So think of this as powers of 2, 1, 2, 4, 8. So 1011 gives you 11. 0110 is 4 plus 2 is 6. 1110 is 8 plus 4 plus 2 is 14. 0001 is just 1. 1000 is 8. And 0100 is 4. So that gives you the decimal equivalent of the chromosome value. The decode used is C over 10. So why is C over 10 a suitable decode? What is C over 10 going to deliver? Because remember, the binary strings are just coded representations of the design variable. So what is C over 10 going to deliver?
Wow. Fitness. Yeah.
Okay, the decimal equivalent. So C over 10 is going to deliver the value of the design variable that each chromosome represents. Because since the chromosome values can go from 0 to 15, when you divide by 10, you go from 0 to 1.5 in steps of 0.1. So the decode always delivers the corresponding design variable. So for this one, it's particularly simple. So we've got 1.1, 0.6, 1.4, 0.1, 0.8, and 0.4. So that gives us the design variable. So the next thing is to determine the fitness, so how well each of these design variables meets the objective of minimizing the function g. So the fitness function chosen is 1 minus g. So the bigger g gets, which is bad news, the smaller the fitness function gets. So running down the values of G, which we need to compute the fitness, then here is G, so plug these values in, and I get 0.188, 0.004, 0.538, 0.321, 0.018, and 0.071. So those are the 6 values of the value G, and then the fitness by definition is 1 minus G. So that gives me 0.812, 0.996, 0.462, 0.679, 0.982, and finally 0.929. So those values there give a relative measure of the fitness of purpose of these 6 values of the design variable. So what's the next stage?
Relative fitness.
Okay, relative fitness. For that we require the population fitness. So that's this last box here. So I think if you add those fitnesses together, the sum is 4.86. So that's a measure of the fitness of the entire population. So that now allows you to calculate the relative fitness, which is the absolute fitness divided by the population fitness. So I get 167.205, 0.095, 0.140, 0.202, and 0.191. And that should add up to 1, thereabouts. And why are we calculating the relative fitness? What's the reason for that?
Find the percentage of it.
Yeah, okay, I'll go with that. So given that the total of the relative fitness is 1, each of the relative fitnesses effectively gives us the percentage of the roulette wheel that each of these designs is going to accommodate. So, as ever, we've got a wheel, and the first cumulative relative fitness is 1/6, which is about here. So that's the first design. If we add 0.205 to that, we get 0.372. 0.372. So that second wedge is design 2. If we add 0.095 to that, we get 0.467. So not quite such a large slice. So that's 0.467. If we add 0.140, we get 0.607. So somewhere around here. If we then add 0.202, we get 0.809. So we're up here somewhere, 0.809. And then finally, when we add 0.191, we get 1. So there is solution 6. So it's pretty shockingly drawn, but what the cumulative relative fitnesses give us are the break points on a roulette wheel where we consider the circumference to be 1. So, next step.
Take 2 numbers.
Okay, so we've got to select first. And we select by spinning the roulette wheel how many times?
Spinning.
6 times.
6, because we have a population of size 6, so we need to create 6 new designs. So 9342 lies in the final segment, so that must be solution 6, which is 0100. 2644 lies in the second segment, so that must be design 2, 0110. 1603 just lies in the first segment, so that must be design 1, 1011. 8729 lies in the final segment, so that is again design 6, 0100. 2379 lies in the second segment, so that's design 2, 0110. And finally 6458 lies in the fifth segment,
1000.
so it's design 5, which is
1000.
1000. So according to fitness, we've just drawn solutions from the current population. So the next step is crossover. So we're told the crossover fraction is 1/3, so what does that mean?
You multiply 6 and then you take 2 from it.
Yeah, so basically that means 1/3 of the population that we've just drawn through is going to be selected for crossover. And the assumption is that each of these designs, in terms of crossover, has exactly the same probability of 1/6. So the breakpoints are 1/6, 1/3, 1/2, 2/3, and 5/6. So we want 2 solutions, so we have 2 random numbers. So the next number is 9669, which lies in the final interval. And 6649 just lies in the fourth interval. It's slightly less than 0.666 recurring, which would be 2/3. So those are the 2 chromosomes we've selected for crossover. So how many possible positions for crossover are there?
5.
Right, there are 5, because we have 4 bits, so there are 5 possible points we can split the chromosome. So the assumption is that the breakpoints are 0.2, 0.4, 0.2, 0.4, 0.6, 0.8 and 1. So anything up to 0.2 will pick the first one, between 0.2 and 0.4 the second one, and so on. So the next number is 8704, and 8704 is greater than 0.8, which would imply we're picking the rightmost split. So we take the head of one and the tail of the other. Well, we're taking the whole chromosome. So chromosome number 4 becomes 1000, and chromosome number 6 becomes 0100. Because we put the head of one on the tail of the other, but since it's the whole chromosome, they just change positions. And then finally, we have a mutation fraction of 1/12. So, what does that mean?
You multiply the number of the bits and then you have 3.
So mutation is about the bits, not the chromosomes. So the total number of bits here is 6 4s are 24. And with a mutation fraction of 1/12, that means we're going to select 2 bits at random to mutate. So 2 bits, and they all have equal probability, so it's the breakpoints are 0, 1, 1/24, 1/12, 1/8, etc. So 0099, that's going to be the first bit, because I think that's less than 1/24. So this breakpoint here would be 1/24. So we're going to pick the... Well, another way of doing it is multiplying the number of bits by the random number and taking the integer part. So 24 times 0.0099 is going to be less than 1, so the integer part of that is 0, so it's the first bit. And then finally 1370. What's that times 24?
It's going to be 3.
Don't wait for me to do it in my head. Wait for someone else to tell me.
3.288.
3.2, okay, so it's 3.2. So it's going to be number 3, so 0, 1, 2, 3. So it's going to be this one here. So the two marked bits are marked for changing, so we end up with 1101, 0110, 1011, 1000, 0110, and 0100. And of course, each of those solutions will correspond to a value of the design variable. So you repeat the process. So that is that's the GA. So you should be starting to get the hang of the manual calculation, and you know, without giving away any trade secrets, that's the limit of any hand calculation in terms of GA that you'd be expected to do.
What calculations do you do with
Okay.
Mutation.
you have 112?
Yeah, 112 multiply the bits, 24.
So are there any
Yeah,
queries or
for
questions on that particular example?
Can I just ask,
Yeah.
Professor?
Yeah.
When you took the mutation and then one of the values comes 0,
Yeah.
so we still have to change the chromosome, or the chromosome, you know the mutation.
Yeah.
It's 0.
So yes, look, the two chromosomes. Sorry, the two bits that I've highlighted with a crudely drawn rectangle. Those are simply the bits that have been selected by the two random numbers to be mutated. So they will then get changed to 1 because their current value is 0. If they'd originally been 1, they would have got changed to 0. So the random numbers are simply selecting which bits you're going to mutate. It may be, suppose you selected the same bit twice.
Change it and then change it again to the same.
Precisely. It means ultimately you'd mutate once and then mutate a second time, so you'd revert back to the original value of the bit. Which seems obvious, but yes, that's exactly what happens. Yeah.
So let's take a question.
1/24.
Multiply by 12 so I can get a scale, but what is it?
Because we have
choosing,
mutation, we're looking at
it's my random
individual
number
bits,
between 0 and 1.
and there are
So
24
I
of
put in a
them.
scale on it. So it's
They all have equal
all the
probability
chromosomes
of being
24,
selected.
Let's say 100%. And
So
then
that means each of them has a space of 1/24 on the roulette wheel of life. So the first bit, anything from 0 to 1/24, we'll pick the first bit. Between 1/24 and 2/24,
yeah.
we pick the next bit, and
This is
so
the
on.
mutation. Okay? What I do is I take 112.
The 1/12
because I've got 24,
told us how many bits we were going to
6
select.
chromosomes, 4 bits
Yeah.
each.
So
22
if
bits,
the mutation factor, for example, had been 1/3, what would that have meant?
So I take my first random number.
Yeah.
And what
So we would have taken 8 random numbers between, because 1/3 of 24 is 8, so that meant we're going to mutate 8 bits. So we take the next 8 random numbers, identify which bits they represented, and switch those bits. So, okay, but the probability would still be, the intervals would still be 1/24. It's just we'd be selecting 8 instead of 2. Okay.
crossover function 1/3.
Okay, right.
For mutation, you take 2 chromosomes. One. So we took this one.
Oh yeah, because it's mutation. Alright, so it's 1/3 times 24. 24
Equal
equal to 2. I take 2. So that I take only 2. Okay. And for crossover, it's the same. It's 1/3 times 6. So only 2 places.
So this is a question on
So the 1/3
sheet
times 6. That's the
6,
number of
which
places
is
I
the
cut.
particle swarm optimization, and just looking at question 3 here.
Sorry.
So we're given some information about particles, and we're told that there are 4 particles located at 1, 1, 0, 2, 0, and 2, 1. And you're given a picture. So we've got a particle at 0, 0, a particle at 1, 0, a particle at 2, 0, and a particle at 2, 1, which is about there. So that's our 4 particles. And they're sitting in the design space of this objective function. So I think you can appreciate that's a set of concentric circles as denoted by the picture. And we're trying to determine the local, or determine the minimum of f of x, y. So I think without too much calculus, you can determine it's where the x is at 0, 1. So each of the particles has been given an initial velocity. So the first particle's a half 0, so it's it's moving in that direction. The second particle is 0, 1/2, so it's moving in that direction. The third particle is minus 1/2, 0, so it's moving in that direction. And the fourth is 0, minus 1/2, so it's moving in that direction. So those are the pseudo-random velocities assigned to the 4 particles. So you're given a fitness function, so why might it be a reciprocal of the objective? Yeah, because we're trying to minimize the function, so the fitness of any of these particles has to so the particle defines a point in the design space, and the fitness must reflect the fact that particles where f of x, y is less must be fitter, must have a higher fitness, because they meet the objective more closely, so hence the reciprocal. And we're given the PSO parameters. So implement 3 steps of PSO. Well, I'm not going to implement 3. Let's just try and squeeze 1 out. So, what's the first thing that we need to do for particle 1, 2, 3, 4? So I'm going to assume we've already got note of the position and the velocity. So we need an expression, we need values of 1 over f, because that's going to give us the fitness. So the first particle sits at 0, 0, so the value of f is going to be 1. 1 over 1 is 1, so the fitness of the first particle is 1. The second particle sits at 1, 0, so x is 1, y is 0, So the value of f is 1 squared plus 1 squared is 2, and the reciprocal of that is 1/2. The third particle sits at 2, 0, so x is 2, y is 0. So we've got 2 squared is 4, plus 1 squared gives us 5,
0.2.
and the reciprocal of that is 0.2. And finally, the final particle sits at 2, 1. Well, clearly, if y is 1, the second part of f is 0, so we get 1 over 2 squared, which is 1 over 4, which is 0.25. So those are the fitnesses of the individual particles. And I think you can see, looking at the picture, yeah, the first particle definitely is inside the smallest concentric circle, which would imply it's the fittest. And the particle, where are we? Particle 4, where are we? No, sorry, particle 3. Apologies. Yeah, particle 3, we can see sits outside, is clearly sitting just outside this circle, and all the other particles sit inside this circle, so this must be the weakest particle, and yes, its fitness is 0.2, which is the smallest. So what do we need to determine now? Well, the easiest thing to determine first is the global best, which is going to be particle 1 at 0, 0, and the particle bests, PBs, well, for each of the particles it's just going to be their current location, because we haven't got anything else. So it's 0, 0, 1, 0, 2, 0, and 2, 1. So global best and particle best locations. And once we have that, we can now update the velocity vector of each of the 4 particles by applying the inertial, the cognitive, and the social components of the swarm behaviour. So if we just look at particle 1, so the inertial part is just omega times its velocity. Well, its velocity vector is 1/2 0, and omega is 1/2, so the inertial component is going to be 0.250. So 0.25 in the x direction and 0 in the y. So it's omega times the velocity vector. The cognitive, well, the cognitive is going to be C1R1 times the particle best minus the location of the particle. So what is it for this particle 1? It's going to be 0, 0, not because the particle's location is 0, 0, but because the particle best and its current location are exactly the same. So PB minus X is 0. And finally, the social aspect. So this is how the particle responds to the swarm's best behaviour. And that is C2R2 times the global best minus the current location. And since that particle is the global best particle, its current location of 0, 0 is indeed the global best. So the difference of the 2 positions is 0. So if we add all that up, that tells us that delta V, the change in velocity, is the sum of these 3, which is 0.250. sorry, it's getting a bit squeezed here. So the updated position of particle 1 is going to be the current position, which is 0, 0, plus the velocity, 0.250. So that gives us 0.250. So the particle is going to be at, I don't know, somewhere around here. It's a bit hard to sketch in. So you simply need to repeat this process. That was for particle 1. You need to repeat the process for particles 2, 3, and 4. So inertial, cognitive, social. That gives you the change in velocity, which you can then add to the current location to give you the new position of the particle. So what will you expect to see in terms of inertial, cognitive and social for particles 2, 3 and 4, just in very general terms?
Increase.
Well, the inertial term should tell you that the velocity components are simply going to halve. Oops, sorry, just down a bit. So particle 2 would become 0.25. The fact that this is the beginning of a swarm simulation means that the cognitive component is going to be 0, because the current particle best is the current particle location. But for particles 2, 3 and 4, they will all immediately have a social component, because their current position is not 0, 0, which is the global best. So you should see inertial and social components coming out for particles 2, 3, 4. That will then give you 4 new particle positions. Go back to the beginning, work out the global best and the particle bests. So how would you work out the global best?
You compare with this particle.
Best fitness. Right, not quite. Be careful. It's not necessarily the best position, the best fitness of the new positions. It's the best fitness of the new positions plus the current global best. Because if none of the new fitnesses are greater than the current global best, then the global best position will remain unchanged. So it's not just looking at the current positions. So do remember that. That's just, otherwise you might slip. But if the process is working properly, you'd expect one of the new particles at least to have a better fitness than the previous global best. So it would be updated. And similarly with the particle bests, simply compare the current fitness with the fitness at the current position of the particle best. If it's bigger, update the particle best, otherwise don't. Yeah.
Did you say that the new global best comes from the fitness of the new particle with the highest fitness, or the highest fitness plus your
So at each stage, after the first stage, the global best comes from looking at the fitness of the current positions of all the particles and the fitness of the current global best. Because if none of your new particle positions have a fitness bigger than the global best, it stays the same. If you just compared the fitnesses of the current positions, you might, and they might have different fitnesses, but none of them are better than the previous global best, you might mistakenly update the global best with the best of the current lot, which is actually worse than what you had before. And if all that makes sense, you're going to do this exam really well. Okay, so I think it's probably, I'm going to have to cut and run there. So As I say, next week will just be we'll start off, I think we're in N4 next week, so the final room change. So it will just really start with a very quick summary of all the material that we've covered.
So we're going to finish the exam by Thursday. Do you have lectures or?
No?
Yeah?
No, I'm finished.
But I have lectures.